Yeah, please join me to welcome Reda Bensaid, who is currently a PhD student at IMT Atlantique in France and at Polytechnique Montréal jointly. He will be leaving soon to France, I guess. So he's spending more or less half and half of the time here and there. But he got caught in another snowstorm, April 4th. That's a bit of a surprise. Yeah, and he works on related subjects, many to those that we do also, so like few-shot learning and specific segmentation. So he will be talking about benchmarking, few-shot segmentation, and foundation models. So yeah, floor is yours.
So hi everyone. I will be presenting today my work on a new benchmark for foundation models applied to few-shot semantic segmentation, and this work was done in collaboration with the Sony Research Lab in Stuttgart, Germany. So before I present my work, let me present my team. So I'm supervised by Vincent Grippon and François Leduc-Primo. Vincent in France side, who is a professor at IMT Atlantique and the lab STIC. His main research interests are artificial intelligence, few-shot learning, compression of neural networks, and signal processing. And François Leduc-Primo, who is an associate professor in the Department of Electrical Engineering here in Polytechnique Montréal, and works on computer hardware, on microelectronics, wireless communication. So for my team in France, which is called BRAIN, for a better representation of artificial intelligence networks, we work mainly on 3 challenges. The first one is when we have little hardware, so compression of deep neural networks. Second one, when we have few data, so everything related to few-shot transfer, self-supervised learning, and multimodality. And then when we have few priors for complex signals. So we work on domains like vision for classification, segmentation, and so on, neuroimaging for everything related to brain signals, and etc. We work also on audio. And recently we started working on the text in multimodality for zero-shot learning. We are a team of 6 professors and 17 PhD students and 1 postdoc. For the Canadian team, François Leduc-Primo Lab, we are a team of 14 researchers between master's, PhD, and postdoc. And the main work of our team is efficient deep learning, wireless communications, energy efficiency in correcting errors, and in wireless networks. We've seen recently the emergence of many foundation models, both in NLP with, for example, LLMs or BERT, etc., and also in the vision domain, with models ranging from general ones in self-supervised learning like Dino or mask autoencoders to more specialized one like segment anything for segmentation. And when looking at these models, we've seen that many works have been done in adapting these models for few-shot classification, both in few-shot and zero-shot classification, for example, for CLIP. And for example, here I put a work with a recent paper, Closer Look, where they tested normal models and compared them with the recent models like Dino and CLIP. But actually, when looking at these foundation models on few-shot semantic segmentation, the domain is still quite unexplored, so we decided to work on this domain. So our idea was to first propose a standardized benchmark for few-shot semantic segmentation using foundation models, where we will compare several foundation models with several adaptation methods on several data sets, and to try to understand what works and what does not work for these models. So for the standard few-shot semantic segmentation benchmarks, we have a pre-trained model, and then we have a support set. For example, here, 3-way one-shot support set where we have 3 images with binary masks of 3 classes, and then having a query set, we have to segment the instances of these three classes in this new image. The problem with this benchmark is that it supposes that there is no intersection between the classes of the base classes of the pre-trained model and the novel classes. And actually, this is quite difficult to suppose for a foundation model, which was trained on a very range data image, wide range of images. And for example, for some models, we have hundreds of millions of images trained, even though we don't have masks trained with these models, but they've seen all the possible instances. So we can suppose an out of distribution for these models. And the second thing, we want to be able to work also on images where all the image is segmented. For example, we have multiple instances like the semantic segmentation datasets. And for that, we created a new benchmark where in our case, we have a support set, for example, the n-way k-shot. In our case, the way is just the number of classes of this data set. For example, working with cityscapes, which contain 19 classes, we just have 19 way. And the k-shots, for example, if we take the one shot, we just assure that in image one, we have class one, at least. In image two, we have class two, and so on. Even though, of course, there is an overlap of classes, because in image one, we will have other classes. And so we make sure that in every image, we have at least one instance. And so in our support set, we will have exactly k multiplied by n images. And the query set, in our case, will be just the validation set or the test set. For the metric of test, we decided to work with the mean intersection over union of all the classes in this data set. So we decided to work on three known data sets. The first one is cityscapes, which is quite known in semantic segmentation, which contains 19 classes, 3,000 images for training, where we will sample our support set, 500 images for validation, and 1,500 for testing. And these are high-resolution images of images in the streets taken by a car. The second data set is the COCO data set, which contains 80 classes. So it's a quite big data set with more than 100,000 images for training, 5,000 for validation, and 40,000 for testing. And these are lower resolution with a variable resolution ranging overall, the standard resolution is 640 by 4080. And the last one is a more specialized data set, which is the PPD for plant phenotype data set, which is a quite simple data set containing just 800 images. And we decided to work on the simplest task, which is just segmenting foreground versus background. And since there is no conventional split for this data set, we fixed a split, and we took 50% of the images for training and 50% for validation. And the resolution of images is around 500 square images. So for the models we decided to test, we have two multimodal foundation models. The first one is the segment anything, which contains an image encoder, prompt encoder, and the mask decoder. Since we want to work directly on images, and we decided to work on a unimodal task, we decided to take only the image encoder for this task. Same for clip. There is an image encoder, text encoder that are trained jointly with the contrastive loss. We decided to take only the image encoder in our case. We took also some unimodal models. For example, here we have two SSL models, Dino V2, which is the newest version of Dino. Here we have the Dino architecture, where we have the teacher and the student. An image, we take two views of images. In general, it's two crops, and then one goes through the student, one goes through the teacher, and then we try to minimize the loss between the two. And so we take the student in this case. Mask autoencoders, where we have an image, we mask patches of the image, and then we try to reconstruct these patches. So it took the same encoder. And finally, we took a standard semantic segmentation model. It's a fully convolutional network with a ResNet 50 backbone. So we decided to take this Redmi 50 backbone. In this case, it was trained on the Pascal VOC dataset. For the adaptation methods, we tried to test on a wide range of adaptation methods, ranging from linear probing. The first one, which we call the linear method, we just take the output of the foundation model or the model in general. We apply a batch normalization and the conv11 layer so that at the end we will have this number of channels equal to the number of classes. And then we will train only this convolution and batch norm. The second one, which is the multi-layer method, is that instead of giving just the output of the model to this decoder, we take the 4 last blocks of the model, we concatenate them, and we give that to the decoder, which is still a convolutional 1-1 and batch norm. And then we tested some fine-tuning methods. The first one is called the singular value fine-tuning method, SVF here. And we have a segmentation head. In our case, it's still the normal segmentation head, which is a batch norm plus convolutional 1-1. And instead of freezing the backbone like earlier, we decide to we apply an SVD decomposition of the weights of this model, and we only fine-tune the singular values matrix. And it's inspired. It comes from a paper, Lurapes 2022. Second method of fine-tuning, partial fine-tuning, is the LoRa method, where we have our pre-trained weights, and then we add some low-rank adapters, and we only train these adapters. And the last method is the full fine-tuning, where we fine-tune the whole model. For the implementation, actually, what we do for the partial fine-tuning is that we train the segmentation head with the linear one until we have a trained segmentation head, and then we apply these methods. So at the end, we will have a pipeline like this. For example, here for the linear method, we have support set images that goes through the pre-trained backbone. So we have support features. We train the batch norm and conv11 with the support set masks. We do back propagation. And then after that, we fix, and then we have query images and just inference to have our masks there. So for implementation details, since we have images containing overlaps, for example, of classes, the choice of the support set is very important. So we decided to do 3 runs because at the same time, for every run, we have to do some training, so it takes time. So we decided to do 3 for every combination of dataset, model, and method. For the pre-processing, it's the same pre-processing. It's detailed in the paper, but we took normal pre-processing for semantic segmentation. And then we resize the images to 1024 squared because SAM only takes images of 1024 squared. And since CLIP and ML only takes images of 224 squared, we decide to resize the images for this size, and we will talk about this discrepancy later. So for the learning rate, for the linear and multi-layer methods, we just took learning rates that are usually used for these data sets. And for the fine-tuning methods, we decided to do a grid search for the SVF, LoRa, and fine-tuning with 5 values. So we tested with these 5 ranging from 10-2 to 10-6. And then, of course, we take the best one. And for the size of the models, for the vision transformers, we worked with the base model containing around 80 million parameters, and we have a Resnet 50 containing 23 million parameters. So our first results on the one-shot setting, we can see that Dino clearly outperforms by far the other models in all the 3 data sets. We can also see that some gives good performance, since we expected to give good performance because it's a segmentation model. But on the COCO dataset, it gives very poor performance. And the third thing we can see here is that the SVF method overall is the best method between these models. But the standard deviation between the methods is not very big. So, for example, here, if you compare these 3, they are pretty much equivalent in terms of performance, even though sometimes SVF works better, sometimes, for example, we have other methods that works better, especially with more shots. Here, with 2, 5, and 10 shots, we can see, for example, that the fine-tuning method sometimes works better since we have less overfitting. We have the same remarks, DynoV2 still way better than the other models. Some is still very poor on the Coco dataset. And here, for example, you can see for the best method, which is the SVS method, that we take the SVS method, we can see that DynoV2 is better. And these models here are quite equivalent. And for the best model, which is DynoV2, we took the 5 methods, and we can see that the standard deviation between the methods, the difference performance between the methods tends to be lower when more shots are available, meaning that, for example, for 10 shots, they are almost equivalent. And we can see also that fine-tuning scales a little bit better since it is less prone to overfitting with when more shots are available. So for here, we decided to do a study on the learning rates since we did the grid search to compare the best learning rates per dataset. And what you can see here in this table, for example, for a certain method and a certain model, we take the best learning rate for a dataset, and we compare the performance when taking this learning rate applied to another data, compared with the best learning rate of another dataset. And we compare the drop of performance between these two. And we can see that, for example, when we see the squares here between Cityscapes and Coco, that is quite resilient, meaning that if we take the best learning rate for a certain method and a certain model on dataset and with Cityscapes and we apply it on Coco, or the opposite, we have almost zero performance. So the best learning rate for a dataset is the same for the other one. It is not it is not always the case for the PPD dataset because it's a small dataset, and the choice of these support images is quite important. So for the PPD, we have a high standard deviation between the runs, and so it is quite unstable. That's why we have sometimes big values here. Since we don't use the same resolution for other models, the idea was to see if it's fair to do that. And one method is, since the blocking parameter here is the positional embeddings of the model, we decided to just do a standard method of interpolating these positional embeddings so that we can feed high resolution images, for example, to clip and ML. And we can see that when doing that, actually, we have lower performance with high resolution images than in low resolution images for clip and for MAE. But for Dyno, it tends to scale better because the explanation is that clip and MAE were trained with a fixed resolution, and Dyno V2 was trained with the variable resolution. So for that, even though we work with high resolution images for Dyno V2 and low resolution images for clip and MAE, it is fair to compare them because we have a drop of performance when trying to do the same resolution. Here, we decided to compare to orthogonalize the different components of the model to see what component is responsible for the good performance of these models. And since these are pre-trained vision foundation models, we can just fix a parameter and train that. So we just took off-the-shelf models and tried to orthogonalize to our best. So here we compared the model size, since we have multiple model sizes for these models. For some, we take the vision transformer base, large, huge. For Dyno, we have the small and the large, and then for the ResNet, we have the ResNet 101. And we can see actually that taking the base model, which is here first line and here is the second line, is a quite good trade-off for the linear method, meaning that having bigger than the base model doesn't necessarily mean better performance overall, or if it's better performance, it's quite negligible with knowing that the large is 3 times bigger than the base. It is less the case for the LoRa method because these models are more flexible when we try to fine-tune these models. For the training dataset, we to try to fix all the other parameters and only see the trained dataset. The best comparison was between Dino V1 and Dino V2 because the main difference between these two is that Dino V1 was trained only on ImageNet and Dino V2 was trained on a way bigger group of datasets, around 140 million images with created and uncreated images. One thing to note is that there are other differences, but there are pretty minor differences compared to the dataset difference. And we can see here that clearly the dataset is responsible for the performance of these models. We can see that Dino V2 outperforms Dino V1 by far. Third thing is the architecture, where we compare the vision transformer with the ResNet. We have two possible comparisons. We have the clip vision transformer base and clip ResNet, and we also have the Dino V1 and Dino ResNet. Here we have the small one, and we took the small one because it's the same size as the ResNet 50, and we can see actually that having a vision transformer transfers way better than having a ResNet. One other parameter is the training method. Here we decided to compare Dino V1 with MIE since they are both pre-trained on ImageNet. They have the same architecture and the same size. They are both vision transformer based models. And here, actually, the training method it is not clear which one is better because Dino V1 outperforms MIE on two datasets, but mask autoencoder outperforms on the COCO dataset. And one last thing is called the registers. Actually, it comes from a recent paper. It's an iClear 2024 paper called Vision Transformer Need Registers. And the idea of that paper is that when Dino V1 was released, the feature maps were quite interpretable. So there were works doing directly, for example, unsupervised segmentation on the feature maps directly of Dino V1. And when doing this on Dino V2, it tends to have a lower performance. So they tried to understand why it is the case. And actually, they found out that in the feature maps of Dino V2, there are some specific tokens that have higher values. And when doing the analysis, they found out that the model tends to store some global information in these tokens. Since there are background tokens on the models, see them as useless, so it stores on these tokens. And so the idea of the paper is that if we give the model some tokens like the CLS token in the input and just in the, we don't use them in the output, just to give them to give a model a place where to store global information, it tends to give better performance and remove these high normal tokens. And actually applying that for Dino V2, since Dino V2 with registers was released, we can see that overall adding registers gives good performance. And so the key takeaway of this part is that the dataset is the most important part, since Dino V2 have by far the biggest dataset in all these foundation models, and that having a bigger model is not necessarily a better transfer, and that vision transformer base is quite a good trade-off for transferring. And one last thing, since SAM gives a very bad performance on COCO, we try to understand why it is the case. And we came up with two hypotheses. The first one was the decoder limitation, because for SAM, it is jointly trained with the image encoder, prompt encoder, and the decoder. And since we isolate the encoder, maybe it is this is why it performs poorly. So what we did, we took the decoder of SAM and we give them a standard prompt. Actually, it is done in some papers. We've seen that, and we try to fine tune the decoder. But actually, doing this with only few shots gives a poor performance and even a worse performance than just having a linear layer. And the second hypothesis was the mask distribution. Actually, in some paper, they computed the distribution of masks in the images of these datasets. And actually, in COCO, there is a clear center bias of the masks in the dataset compared to the SA1B, which is the dataset of SAM. And so we tried to do some augmentations of the image so that we remove this bias, but actually even when doing that, we didn't have better performance. And thank you for your attention.
Thank you, Reda. Any questions? Yeah.
So I saw that for one of the data sets you said like you have 50% for train and validation, but I guess you are working on Fuchsia, and I don't know if you said like how much what is the size of your validation set, because you are doing grid search on learning rate, so you are using a validation set. So what is the size exactly when you are doing Fuchsia?
Actually, yeah, this one. Actually, the training set is where we sample our images. So here we have 2 images, and actually we use 50% of the validation set for the grid search.
Yeah, but when you are doing Fuchsia, like because you have like 400 validation data. So when you are doing Fuchsia setting, when you have like when you are training with one shot, adapting with one shot, what is the size of your validation set that you use to
actually the validation set is the whole the query set is the whole validation set. Yeah.
Is the whole validation?
Yeah. The training set is where we sample the support set, and then the validation set is our query set.
So you took the whole validation set.
Yeah.
Find the
actually, when we test on the whole validation set.
To find the best layer.
Yes.
Okay.
Other questions? Yeah.
These are easy questions because I don't work with Fuchsia. So you don't have test set, it's just like the validation, and then you apply the same to test?
Actually, we have a support and the query set. We train on the support, and then we test on the query. And in our case, the support set is sampled from the training set, and the query set is the validation set. So we just, when we test our performance, it's on a validation set.
But this set is used to tune something?
Actually, since it is used to tune the learning rate, we test on the test set.
If I may, I don't know if you can hear me.
Yes.
Yeah. So I think the question is about like in some papers they use a validation set for few shot, like it's what they do with the core benchmark, for example. But we don't use any validation sample here. Like we only have one shot, and that's all we can use. And there's no validation per se. I guess the experiment that you did with varying the data set, where you train the best hyperparameter on one data set and then you transfer to another one, is what is closer to using a validation set. But yeah, there's no validation per se. It's what you call validation here is just the test performance.
Yeah. And actually, that's why we did this study. In this study, actually, the key takeaway is that if we check the best learning rates, for example, for a fixed model and a fixed method, the best learning rate on a data set gives good performance on other data set as well.
Other questions?
Since you are using, for example, Laurent adaptation and you are comparing different models, so you proceed with search to find the best learning rates.
Yeah.
But to make the comparison fair between the different models, did you make sure at some point that when you are using Laurent adaptation on different models, you fine-tune the same rate of parameters between models? For example, if you use Laurent adaptation on one model and you fine-tune like 10% of the parameters on one model and 2% of parameters on another model, it's not fair to compare the models if they are not fine-tuned with the same amount.
Yes.
Did you proceed some research to find some optimal rank for the Laurent adaptation, or you just put the same rank to everyone?
Actually, it's the same rank to everyone. I think it was 8 or 16, yes. But it's standard.
And there is no like I don't know, for example, if you use clip with vision transformers, you can put like a long adaptation on every module in the attention modules, query, key values, whatever. And I don't know, for example, on the full convolution networks, since long adaptation are more fitted to linear layers, I don't know if you have the same amount of possibilities to put long adaptation on, and you probably have less fine-tune parameters in terms of rate of number of parameters in the different.
Actually, since 4 are transformers, they are equivalent. We did that on the query key and values of all the matrices. But for the convolution, we did that for all the convolutions. But we didn't compare the percentage of parameters between the convolution and the vision transformer. We didn't see that.
Other questions? So it seems one takeaway is that Dino is the best foundation model for few-shot segmentation. Is there maybe a chance that there is some data leakage, let's say, in Dino data to all the few-shot tasks?
Actually, in the pre-trained dataset, there was images of cityscapes. So
in Dino.
In Dino, yeah.
And in the others, maybe not.
No, in the others, maybe not. So we mentioned that in the paper, but for example, even in Coco and the PPD, there's no leakage and it outperforms the other model.
So it has some cityscape.
It has some cityscapes. So for cityscapes, we can say it is not 100% fair, but for Coco, it is fair and gives better performance.
Yep. I don't know if you can hear me, but I have a question.
Yes, Christian.
Oh, great. Okay, so first question, is this study available in a paper? Maybe I missed. Is there like a paper on archive or published where we can see those results, which are very nice, by the way?
Actually, I just updated the archive version 2 days ago, so the paper is available on archive, yes.
Okay, is the same as the title of your talk, I guess?
Yes, it's the same, yeah.
Okay. And then my second question is, because I'm not 100% familiar with the few-shot segmentation literature, but it seems like the numbers that you report especially for Coco, are very low. Even the best performing method is like around 30% mean IOU. So I'm wondering, like, is that okay? Maybe.
No.
What are the values? Like, what's the best?
Actually, it's around 25% in the one-shot setting. Actually, I give the detailed results in the paper, but yeah, on Coco we have quite poor results.
Okay, so it's kind of like your study is kind of like saying which method works better, but like, are these numbers? I mean, is it actually usable? Like 25% doesn't seem like a lot. Have you, like, what's the takeaway in terms of, and even when you show like the trend where you increase the number of shots, I don't know if you can go to that slide. There was a slide where you increase. Yeah, so it seems to, at least for some methods, it seems to like get stuck at around 50%. Like, I'm wondering, like, what
They suck foundation models.
yeah, like is it hopeless to
I didn't want to
get a good performance? Would this be usable like in any real life setting, or
right now it's not necessarily, it's difficult to compare with standard ones. We compared with the ResNet, but right now taking just one image per class and using a foundation model, we clearly don't have good results. But at the same time, we can't compare with the state-of-the-art cityscapes because it's thousands of images.
Sure.
Even 5 or 10 shots seems to be.
Yeah.
Maybe going to a few hundred will be more reasonable assumption, perhaps. perhaps at this point. If you have completely different data sets.
Yes. But actually, we are not that far from the state of the art, even with, for example, the Dino V2 with 10 shots. We are around almost at 70%, knowing that state of the art is 86%. So we're not that bad, even with the 10 shots or 5 shots.
On Coco? Not on Coco.
No, not on Cityscape.
On Cityscape.
Coco, the state of the art is lower. It's 60 or
Yeah,
65.
much lower.
Yeah.
And then when you look at the actual, when you try to visualize the segmentation results, like, do you see that it's kind of like focusing on very obvious things, like, you know, if the object is a person, it might just look at skin color and then like try to extract anything in the image that has this color, or is it like more subtle than that?
To be honest, I didn't go into the visual details, but overall, the models performs in some classes way better than in other classes. But I still haven't done an in-depth analysis on different classes to see how it behaves.
Okay. Thanks. That was all my questions. Thank you.
You're welcome.
We have more questions? Yes?
Sorry.
Please, we have time.
So the first thing is like when you do LoRa fine-tuning, do you apply some kind of balancing on the training, the loss for training? Because, for example, you are dealing with segmentation, and like Cityscape and Coco, for example, they're going to be unbalanced for example, sky and driving roads, because for example, Cityscape is driving roads and this kind of stuff. So you need to balance the loss when you're doing this.
Actually, we don't. No, we don't balance the losses. So yeah, the imbalance can be a problem.
And also for Coco, I saw one paper really recent. I don't remember the name, but they said that the Coco annotations for segmentations are really bad.
Oh yeah.
Yeah.
Okay.
So probably what maybe is happening is that like you have a good insert, but the ground truth is bad, and you are having problems to calculate the MIO.
But Coco is challenging anyway for segmentation. Always it has the loss. And Cityscape is perhaps relatively easy because it's the same setting for all the images. It's just straight scene, so we have the same classes. Pretty much. That might be the reasons.
Actually, that's why we took the PPD dataset, which is a very easy dataset, Cityscapes, which is in the middle, and Coco. Yeah. And for example, for the PPD, with just one shot, we can have better, around like 83-84% of MIO with just one shot with that.
Okay, no more questions. Yes, we could thank the speaker. Thank you.